Hello, everybody. Thank you so much for coming. My goal here today is to give you a flavor of the kind of research we are doing in our lab, the Responsible Data Science Lab. And the title of my talk is Explainability, Robustness, and Fairness in Data Science Applications. Okay. So I'll walk you through a couple of my projects at a very high level and feel free to ask questions as you go. I'll start by stating the obvious that algorithmic decision making systems have taken over our lives, right? They and rightly so, right? So they help us decide who is going to get extra medical care, who is going to be prescribed what kind of medicines, who is going to be sentenced, who is going to be bailed, who is going to be hired, whose loan is going to be approved. These consequential decisions and also your everyday decisions like what movie should you watch, what songs should you listen to, what products you should be buying, right? And rightly so, because these systems have been shown to work very well across domains. However, with their high accuracy, with their sophistication comes a price that they are more often than not, they are highly complicated, which makes it difficult to understand what goes on in these models, what goes on in these algorithmic systems, right? So their complex architecture, the proprietary nature of their algorithms. Some companies do not, open source what the algorithms are. So it makes it difficult to debug these algorithms. So what happened? What went wrong? If something goes wrong, why did it go wrong? How can I make it better? So all of these are issues with understanding or explaining these algorithmic decision making systems, right? And the big uh, term bias, right? So these algorithm systems have been shown to show adverse effects, adverse results on different subgroups. There have been time and again, there have been different examples across hiring, across medical care, you name it, and perhaps machine bias. This was the article that prompted the whole discussion around fairness. Okay, so which brings us to the topic of our talk today, which is what are the pillars of modern day algorithmic decision making systems, and fairness, explainability, and robustness of these systems is what we are advocating for. This is my research, and I'll walk you through a number of projects here. Right. So first of all, why does it matter? Who cares? Right. We'll talk about that. But to give you a flavor, I work on this entire data science pipeline, starting from data collection, data pre-processing, what kind of data sources are you acquiring, what do you do with that data, how do you model, how do you make the predictions, and how do you use those predictions to evaluate something, get some insights. So I work along this entire pipeline. I look at the impact data quality, data preparation has on decisions. I look at how we can make these systems, the pipelines, more transparent, more explainable. And my goal is to remove bias from data because these are data-driven systems throughout the data lifecycle, right? But who cares about all of this, right? I'll tell you who cares. The number one uh, stakeholders are the users, right? Users who are impacted by these systems. What went wrong with them? If somebody gets an adverse decision, what went wrong? What can they do to make it better? Developers, right? So understanding these systems, making them better helps developers diagnose them, monitor the performance throughout their life cycle. Practitioners who maybe do not develop the systems but use them in their everyday lives, right? So understanding these systems would help them debug any off-the-shelf Python packages, for example, that they're using. And finally, businesses, right? Businesses that deploy these kind of systems in their products, they are required in some jurisdictions at least to generate human understandable explanations, right? And if in case there is any adverse output, they do offer options to redress, options for recourse. Okay. So I'll go through one such work, which is called Lewis, and it looks at explaining black box model outcomes. Right. So traditionally, you would have these your neighborhood banks where you could go and say, "Hey, I want a loan. These are my application, and please, evaluate and let me know if I can get a loan." But keeping up with the times, these banks have moved on to uh, having black box models make those decisions for you, right? So a model would say that this person's May's credibility of returning of paying the loan is 50%. So reject that loan for them. The other person, Irfan's credibility is 87%, which is good. So let's have their loan accepted, right? So we aim at generating explanations for these kind of decisions. Why did the system make these decisions? How does the system decide that 50% is good, this person's loan is rejected, this other person's loan is accepted? And if somebody's loan is rejected, right? If somebody is negatively affected, how can we offer recourse? What can they do in the future such that the loan is not rejected, right? And we came up with two scores here that are based, they are called the sufficiency score and necessity scores. I won't go into the details, the mathematical details of what these scores mean, but on a very high level, what it means is to what extent is an attribute sufficient for a positive decision, right? So for example, if you look at the attribute month here that has a value of 24, saying that the duration of that loan was 24 months, what is the probability that, and the loan was rejected for this person, what is the probability that if the duration of that loan was 36 months instead of 24, their loan would have been accepted? Okay, to what extent is this duration or this attribute month sufficient for a positive outcome? Similarly, we came up with necessity score, saying that to what extent is an attribute necessary, right? So for example, here this person's loan was accepted, but if we look at the same attribute month and we change it from 36, a higher value, to a lower value, the loan gets rejected, right? So the attribute month was absolutely necessary for a positive outcome. So these two scores, necessity and sufficiency scores, they are based on probabilistic contrastive counterfactuals, which could be computed from your data given some assumptions. Okay, so using those scores, we were able to generate some sort of explanations. What do they look like? We were able to generate explanations for the entire data, right? For example, here we would say that the credit history of an individual is most likely to give a positive decision. Okay? That was looking at the model's explanations from the entire data. We could also look at any individual's information and say that for this user, their loan got rejected, and what was contributing. Um, the attribute credit history has a positive contribution. But so on the right hand side, we have positive contribution. On the left hand side, we have negative contribution. So what that means is that staying at this current credit history value instead of a worse value has a positive contribution toward the income. But if they change it to an even better value, they still have a positive probability of getting an outcome. Okay, so for each single user, we would be able to generate local explanations that why did their loan get rejected or why did their loan get accepted. And we could also generate contextual explanations by using the same scores over a group of data, right? So here, for example, we looked at two different groups, females and males in our data, and we looked at the effect of changing the status of checking account and found that improving the status of that checking account is more likely to flip a negative decision for male individuals than for female individuals. So we were able to tease apart some sort of biases by using the same set of scores, right? So these are the kind of explanations that we generated simply by using the three scores. Okay, so that tells you what kind of model you have. How does the model make certain decisions that impact everyday users? That's my and yes, before I move on to the next work, using the same scores, we were also able to offer recourse, right? So we formulated it as an optimization function where we would want to minimize the cost of updating individuals' data and such that the score is above a certain threshold. So for example, for this user, we could recommend that the credit amount was such and such, the savings account were less than 100 Deutsche Mark. And if you have more credit amount, more savings, then this recourse doing so will let them have a positive decision. So the loan would get accepted. Okay. So this was the work that was centered around explainability. And then we moved on to our next work that said, okay, that's great. We can explain models, but can we also look at why models make why behind models make certain decisions, right? So for example, if we have this model that exhibits some sort of bias that is quantified by a number of fairness metrics like demographic parity and so on and so forth, we would want to explain why the model gave this kind of a biased decision, right? And we want to trace it back to the data that the model was trained on. Okay. How we did that is through the concept of identifying root causes of bias, okay? Where we said that if a model is trained after removing some data, right, and that resulting model has a lower amount of bias, then we can say that that part of the data, just by being there, was contributing toward that bias. Okay, so we say that that's a root cause of bias, and to do that, we use the idea of data valuation. That what is the contribution of each data item in my training data toward the end bias. Okay, and this is an expensive computation if you had to retrain models again and again and again for each data items, but we avoided that by using inference functions and machine unlearning techniques, which is a very recent field in the area of machine learning. But inference functions have been there for decades. Okay, so what kind of results we got here was interesting. That for this particular data set, we said that okay, if you look at that pattern where age is more than 45 and gender is female, that's a very small pattern that has a support of 5%, meaning that in the entire data, you would have 5% of the data that are females and are more than 45 years old, right? If you remove that fraction of your data and retrain the model, your bias is reduced by 55%. So that pattern or that part of the data is contributing towards 55% of the bias that you see in the model. Okay. Of course, we do not remove the data, but we inspect them for potential errors. Okay. So this slice or this subset of the data is deemed responsible for some bias. Let's look at it. What are the problems? Maybe the labeling is not done correct. Maybe there are some data quality issues. Maybe we don't know. We'll see. Right. These are the kind of explanations that we generated for debugging bias in the models. Okay. And then I move on to the third work, right? So which looks at, again, task-oriented or goal-oriented model performance, right? So we have training data, we have the model, and we have the predictions, and I want to make this data, make the model perform better. Meaning, if my model has low accuracy, or if my model is exhibiting a high amount of bias, what can I do? How can I make a use of the available data to augment my training data such that the resulting model that I built would be better. It would have lower bias, it would have higher accuracy. Okay. To do that, the approach that we took was that we looked at the entire set of data pool. It's a large data pool. It has a millions of rows, in this case, structured data, but it would work for unstructured data as well. We clustered the data using standard clustering mechanisms, and then we used reinforcement learning. Okay, that has a trade-off between which clusters to explore, which clusters to exploit. Right. So we explore some clusters, choose a cluster depending upon what is its estimated impact on the downstream model performance. And within that cluster, we do not select data points randomly, but we identify what are good data points within that cluster. So we again use data evaluation here, which it was inference functions in this case, that work for some a very specific class of machine learning models. Okay, so once we identify that data, we say, okay, let's incorporate that data into my training data and reevaluate. If it improves my fairness or accuracy or a weighted average of both of these metrics, then good, I incorporate it in the data, and then I look for more data. Right? Keep on doing this until I reach my desired threshold. Okay, and the results for this approach were pretty interesting. The blue lines here is our approach. On the x-axis, we have what fraction of data we have included in our training data, what fraction of the data pool, and on the y-axis we have the fairness metric. So the higher we are, the closer to zero, the better. A negative means that we are doing pretty bad. Initially, when we did not have additional data from the data pool, we just had the training data, we had pretty bad fairness. But as we kept on augmenting my training data with more and more data from the data pool, my fairness started becoming better. Okay, and these are some other baselines that we compared against. And the conclusion here was that if you are very selective about what kind of data you input into the model, you could rapidly reduce bias. You could rapidly improve your accuracy. Right. Okay. So far, the kind of interventions we have done is here, right, where we have the training data, and we say, okay, let's remove data from, remove subsets from this training data and see how our bias, how observe the model bias, observe the model accuracy. Or let's say add more data and see what happens to the model performance, right? Now we are moving a little upstream and considering the entire pipeline, right? So we now look at earlier stages in the pipeline, for example, data acquisition. Here, we make the claim that not all data sources are important. There are some data sources that have more valuable data compared to other sources, right? So we have to be very selective about what sources we grab our data from. Okay, and to do this, we took inspiration from biology, from protein synthesis, and we use something called as gene splicing, right? So where new proteins are synthesized by mutating existing proteins. Okay, so we use the same approach. We maintained two sets, an active set and an inactive set. The model is trained on the active set, has a certain performance metric, and at each iteration, we evaluate each source, right? So are these sources in the active set good? Are they contributing? Are there sources in the inactive set that are better, that could be included in the active set, right? And then we identify what is a bad source in the active set, what is a good source in the inactive set, and we swap them. So we keep the good sources and we discard the bad sources. The goal is that after certain iterations, we converge, and we actually do converge pretty fast. Okay, and what we observed here was that by doing this simple gene splicing, so we have two approaches that we offered here, source grasp and source splice. The blue lines here, which you cannot see, is source splice. And on the x-axis, we have a data set that has a varying number of sources. On the y-axis, we have the number of models explored, meaning how many models have we trained after we add a source or we delete a source, right? So the fewer the number of models explored, the better for us. And as you can see, by using gene splicing, we have explored far fewer models, but achieved the same effectiveness as these other methods that are brute force, right? And some greedy approaches. Okay. So what we showed here was that even by exploring very few models, by doing very few model retrainings, we could compose a subset of sources that would be more valuable for our downstream model performance rather than taking the set of all sources or looking at individual data points. Okay, so we moved from the downstream process to a little upstream. Now we got back to the pipeline and said, okay, this is all great, but this pipeline could also be opened up furthermore, right? So what we did was we expanded. We looked at the data preprocessing stage and said that, hey, this data preprocessing stage is nothing but a system of components, right? So within the umbrella term of data preprocessing, we have missing value imputation, we have normalization, we have outlier detection, we have handling noisy data, we have inconsistency detection, we have deduplication. All of these are exclusive research areas in databases, in statistics, and all, right? So we looked at one such system where, or one such preprocessing pipeline where we had very few components. And we said that, okay, let's see what people do with pipelines, right? And it turns out that people uh, uh, create a pipeline and then try to optimize that pipeline for the data that they have at hand, right? But how good is the pipeline? How vulnerable is this pipeline or is this entire system to any changes that you have in your data? If you change your data, if there is a huge change in distributions, pipeline might not work. At what point does the pipeline stop working? At what point does the pipeline break? Right. So this was the question that we wanted to address in this work. How vulnerable is the system to any changes in data distributions? And how we did that was that we looked at intermediate outputs on the training data. So after each component in the preprocessing pipeline, we observed what is the output. What does the distribution look like, right? What do the profiles look like? What do the data profiles look like after each of the steps and after the entire preprocessing? Okay. We then went back and said that for the new data, for the deployment data, which might have a little different distribution than my training data, what do the corresponding profiles look like? And then we compared them, right? We used simple Manhattan distance to look at the data, the difference between the two data sets, the two data profiles. We looked at KL divergence, again, to see how the distributions compare against each other. And by doing so, we were able to come up with vulnerability scores for each pipeline component, saying that this missing value imputation component is vulnerable to any noise beyond 10%. So if you have 10% of missing values, this component would work fine. Or if you have up to 5% of outliers, this component would work fine. But the moment you have, let's say, 7% of outliers, you would need to do something with the pipeline. Maybe you need to retrain, maybe you need to reconsider what is going on in there, right? So we came up with vulnerability scores for each of the components, and then we used those scores to come up with a vulnerability score for the entire pipeline, saying that this pipeline is vulnerable to missing data or to outliers or to some other kind of noises. We quantified that, right? And what did we do with that kind of quantification? We made recommendations. We said that, okay, this pipeline exhibits a vulnerability score of 7, which means that any shift in the training data will likely result in a decline of the model performance by 3 to 5%. Right? We also said that most vulnerable, we also identified what is the most vulnerable component. And then we proposed some interventions saying that if you change the missing value imputation, from mean imputation to median imputation or to KNN-based imputation, the many strategies that you can use for missing value imputation, you would be preserving model performance by and large. Okay. So that was the work that uh, we had earlier this year. And then we went ahead to further working on the pipeline and saying that, okay, now if we have the same pipeline and the parameters are optimized for your training data, right? How can we optimize these parameters for deployment data, right? So the deployment data might have both the deployment data and training data might come from the same distribution. They might come from different distribution, right? So if the data varies a lot, the uh, the naive solution is that you look at the entire set of possible combinations. That if you have 5 options for missing values, if you have 3 options for normalization, if you have 2 options for outlier detection, then you have 5 times 3 times 2 pipelines. You run them and see what is the best, and that becomes the best for your deployment data. Right? So that's grid search. You don't want to do grid search, that's exhaustive. So we look at the data characteristics, the data profiles after each step, and then guide the search effectively through Bayesian optimization. Okay, so I cannot go into the details of this work more because it's still under review, but this is the direction we are at right now. So we started with a model, a downstream task that used some training data, right? We looked at what is wrong with the training data. Let's debug the training data. Okay. Then we said, okay, but the data, before it becomes the training data, before it's fed into the model, it goes through a life of itself, right? So there is a whole data pre-processing pipeline that does things to data. You acquire data from somewhere, you integrate them, you remove noise. So what happens in each of these components, in each of these stages, plays a very important role in what happens downstream. So we are opening up the system to its components, right? And looking at each of these components individually. And of course, as you would have realized, each of these components also have a human component, right? So somebody is making those decisions. Somebody is saying that, okay, for missing value imputation, use mean imputation, or for normalization, use z-score normalization, right? So the experience of a human, of a user, the biases of a user manifest themselves into the downstream model performance. Okay, so that's an ongoing piece of work that we are also doing. Right. So what are the opportunities for us? Okay, so what can we do as a combined school of applied and creative computing here? Okay, very interestingly, I found this work in IEEE transactions on visualization and computer graphics, which is not my area at all. But the work, Dead or Alive, continuous data profiling for interactive data science, is exactly what I'm working on. Okay, so the idea is that if you have a data science pipeline, you have some sort of a notebook, right? Could we show snapshots to the end user that, hey, things are breaking here, something is going wrong here, right? So this paper, I've not gone through the paper entirely, so I cannot tell about it, but what we are working on is similar. but from a more algorithmic side. Okay, so we are trying to solve these problems and then show to end user what is wrong, how do we repair things. Okay, so that's one option. The other options that I could think of was that we have our focus in our lab is on data quality, right? So we intend to make um, we intend to ensure that the data that we're using for any downstream, any automated decision making system is highly reliable, gives you trusted decisions. How can we make use of that data to help the end user or somebody, the human that is there, make some decisions, get some insights that they could rely on, right? We do offer provenance, right? So we trace back decisions to the data or the system components, right? So how do the data transformations affect the downstream design decisions? Okay. And finally, how can we make use of interactive exploratory data analysis to help understand what are some usability issues, right? So if there is a human that's using the system, but they are facing issues, right? Issues as in not being able to understand what is going on in the system, how can we help them, right? Who are we making these systems for? Okay. So with that, I will stop and I will probably thank students in my lab. Ike is here. Ike joined our lab this year and is hoping to leave very soon. He's on the way to graduation, and some students are there. A lot of them have graduated, but I'm open for collaborations in this space and using data and how do you use data to help the humans or the end users who are there in the system. Okay. With that, I would stop and I would be happy to take any questions that you might have. Yes, Tawfiq.
Thank you. It's a great presentation. I just was wondering, in the era of machine learning, we had a lot of data for many problems. So saying that I'm going to draw, like, for example, if I have female 10% and 90% male, drawing it from the male, it's actually a loss,
Yeah.
So I was thinking, did you try, for example, to do on the training batch, like you have in each and every training batch, you kind of have same presentation from the two gender, for example, and in that way, you kind of like have the balance between the two genders.
Yeah, so what we realized was that balance simply does not help. So in one of the works, I don't know if it was maybe the selective data expansion. So in that work, we looked at what kind of data you would want to augment your training data with, right? So we looked at, okay, if we have the same number of males and the females, that would solve our problem, but it did not. We said that if we have the same composition, meaning the same fraction of people, women who are getting positive outcomes and negative outcomes, to be the same as the fraction of men who are getting positive and negative outcomes, that would help, but that also did not help. So there's a role of the model here, and it has to be tied with the downstream task. So I understand that if you ensure the data composition stays the same throughout the training epochs, that might help, but we have not explored that. We do not look at individual epochs yet.
If you go to the next slide.
Sure.
How we know that this one is what we are avoiding the memorization problem.
What are we avoiding?
Memorization problem. Because here the fairness is like very big.
Demonstration, I think here we are, once we acquire the data from the data pool, we keep it in the training data, right? Then we get the next batch of data from the pool and we add that. So we are memorizing in a way, right? So does that answer or am I off track?
Yeah, but I'm afraid that this would affect the generalization of the model.
The generalization of the model, great question. So meaning the accuracy of the model, right? So actually, if we go back here in the reinforcement learning, right, each time a cluster is chosen, we update its reward, right? So we update the reward of all the clusters. Now that reward score incorporates both fairness and accuracy. If you only took care of accuracy, this would not work. If you only took care of fairness, your accuracy would degrade very fast. And we had experiments that showed that. Then we made that adjustment.
Thank you.
Thank you.
I have a question regarding the previous one, you, couple slides before this, about is that you remove the data, right? Remove the data and you can find the problem.
Yeah.
But sometimes it's, I think it's really about the meeting the data.
Sorry,
It's the meeting some data. Could really the meeting part, because we didn't collect the data, that could be the root cause. For example, this one, right?
Yeah, the missing data.
Yeah, so here, maybe, I know in the old time, I'm not, yeah.
That's a good question.
Let's say a female, right? When they have kids, so they drop off from the career and they miss about 10, 15 years.
Sure.
Then they come back to back and then they have to start over.
Right.
And then that's called low salary.
Right.
Right. So how to address that part?
So that's a little difficult. Yeah. So what we are saying, what we did in this work was look at a causal way of explaining. So we said that if something is there in the data and now it's not there in the data, right? We know the difference that's causing that could be attributed to the that particular success in the data. Now what I'm saying is that something is not in the data and if you acquire it, right? But that potential, it could be done. The potential set of subsets, what do you consider? And where do you stop? We could think about it, but there are complications that I can quickly think, right? So if you think that some subset is not there, acquire that, but there are other avenues that often need to be taken care of, right? How do they play a role here? It's an interesting idea. I haven't thought about it, but yeah.
Two quick questions. One is for the vulnerable points that you identify in that data pipeline. Anyone using that in the cybersecurity world, would those become, say, kind of a possible attacking point for this pipeline there?
It could be, yeah. I mean, so the whole area of data poisoning, right, poisoning attacks,
Right.
personal data.
Right.
If somebody is aware that this component is vulnerable to noise, right? What's in that noise?
Right.
If the noise is not detectable,
Mhm.
right? But if the noise is detectable, then we have a problem.
Some questions on some of this privacy preserving, right? If we will do some privacy preserving work, maybe we will kind of anonymize some of the data in this. Will that have an impact on the data analysis? Will that create difficulty for this pipeline there?
For the vulnerability part?
Not just in general.
general.
but-
The decision, the insights that you would get would not be accurate, right? As it is, we are doing some approximations in all of these. We are not optimizing it, but we are get close to the optimal solutions. But if you obfuscate, anonymize some part of the data, then the decisions you would make would probably a little farther from the ground truth. I haven't considered that at all, but an idea to start, yes.
Okay.
All right. Thank you.